playlist deals with some aspects of Eurocode 2 Part 1.1 version 2023. Watch this playlist for further selected topics. This video deals with clause 5 and it's about materials. Let's have a look at the design properties. Table 5.1 gives an overview of the compressive and tensile strength of concrete. We see immediately that they have added a higher strength class, the C100-115, which was not there in the previous code. We also see that for the mean tensile strength, there's a new formula for concrete quality bigger than 50 megapascal for high strength concrete, which means that the values of FCTM, upper and lower limits, that they are changed in respect to the present code. The other elements stay the same. It's good to know that all the design properties of concrete that they may be used for surface temperature in the range of -40 and +100 degrees. Let's now look at the modulus of elasticity of the concrete, ECM, the mean modulus of elasticity, equals a factor KE and FCM to the power 1/3. FCM is FCK plus 8, expressed in megapascal. The factor KE, it's for quartzite aggregates, it's 9,500. You have a lower value of 5,000 and a higher value of 13,000. So this is quite a range. Now we can put that in a small graph. X-axis is the concrete quality, and the y-axis is the ratio between the value of the modulus of elasticity according to the version of 2023 divided by the modulus of elasticity according to the version of 2004. So this means that when this proportionality is bigger than 1, then the modulus of elasticity is in the new code bigger. But we see that for quartzite aggregates, it's almost the same. So there's no difference between the two codes because the proportion is, or the ratio is 1. So you can wonder why changing a formula of modulus of elasticity, why the effect is almost nothing. We also see that in the lower limit, the green, in the lower limit, we have 26% less value, and in the higher limit, we have 12% more. Something about creep. The creep deformation of concrete, epsilon cc, at time t for a constant compressive stress sigma c applied at the concrete age t0. So t0 is the time at point of loading. Then the creep deformation is then given by the creep coefficient proportional to the compressive stress divided by the modulus of elasticity. It's denoted EC 0.28, and in the code formula B21 says that EC equals alpha C times ECM 28. So I assume this is a typing error or something like that. So I've added EC28 because EC is defined at age of 28 days. So EC or EC28 is the secant modulus of elasticity, and ECM28 is a tangent modulus of elasticity. We should not make a mistake between those two. For creep, we use the secant modulus of elasticity. For deflection, we use the tangent modulus of elasticity. The coefficient alpha c is given by this formula. We can now put this in a graph for all concrete qualities, and then we look what the value alpha c entails, and we see that it's almost linear, but not quite, but it's almost linear. And when you take, for instance, a quality of C30, you see the difference is something around 12%. So the difference between the secant and the tangent modulus can be, for normal quality of concrete, be 12% higher, which is significant. The creep coefficient at a certain time t, when the loading started at t0, is given in Annex B, and now we will have a look at that. The creep coefficient is the sum of two types of creep, which is the basic creep coefficient and added by the drying creep coefficient. The creep coefficient phi is in fact the mean creep coefficient. So it means that you have a lower limit of 0.05, which is 0.5 times this coefficient, and an upper limit of 0.95, which is 1.5, this creep coefficient. This lower and upper limits are used for bearings, joints, and expansion devices. T is, of course, the age of concrete in days at the moment considered, and T0 is the age of concrete at loading in days adjusted according B17. The basic creep coefficient now is given by formula B6, and then this first part is a function of FCM, and the second part is a function of T minus T0, which is in fact the duration of loading, because the load starts at T0 and the T is the time considered to calculate the creep coefficient. And you see also here there is T0 adjusted, so we have to adjust the time of loading. We will see just now how to do it. Then we have the drying creep coefficient. It's also a multiplication of 4 elements. They are given by the following formulas. They are more or less well known, but they are different from those given in Annex B of the Eurocode 2004. And these are the 4 elements. You see that one of the elements is a function of the relative humidity. It's also a function of the value of Hn, which is the given by this formula, and U is the circumference of the element exposed to the air. The factor gamma T0 adjusted is equal to this formula B14. BH is equal to this, and alpha FCM is this formula. We set RH is relative humidity, U perimeter of structural member, and T min T0 is a non-adjusted duration of loading in days. T0 adjusted is the adjusted age at loading in days, and we can calculate it according to this formula. And the In fact, why do we use the adjusted time of loading? Because it is the effect of early strength development of concrete on the creep coefficient of concrete, and it may be considered by modifying the age at loading T0 to T0 adjusted. For T equals 20 degrees, then T0, T is equal, this one is equal to T0. And for different T different from 20 degrees, then you can use another formula, B18, which I did not put here on the slides. The element alpha SC is given here. And you see, because alpha SC is 0 for cement class, the normal cement class, Cn, which is here the red line. And on the x-axis, you have the time of loading. And on the y-axis, you have the adjusted time of loading. So just to see what is now the mean difference between T0 and T0 adjusted according to this formula. And then you see this is the effect on it. So for normal cement, there's no effect at all. But if you use, for instance, a rapid cement, rapid hardening cement, then you will see that when time of loading is, for instance, something like 28 days, which is the end of the curve, then you will see that you have to adjust the 28 in a number equal to 33 or something like that. So it's not much difference between those two. On the other side, if you have slow hardening concrete cement, sorry, slow hardening cement, then you will see that instead of 28 days, you need something like 24 days to put in the formulas, which is also not a big difference. Because this is almost straight lines, you can approach it by a simplification for 20 degrees. And then T0 is bigger than 7 days, because this one we cannot simulate with a straight line. And T0 is almost more than 7 days in practice, practically speaking. And then we have this simplified formula which can be used. Regarding creep, we can now, all those different formulas, we can now combine them in different cases. And we will consider a slab and a beam. And we will take from the concrete grade, it will take 30 and 50 megapascal. For humidity, we will take 60 to 80%. The age of concrete at loading, we will take 28 days, which is the most normal case. And the age of concrete at moment considered, when we are calculating the creep coefficient, we have taken in this example 50 years. And this is expressed in days. And the age of concrete at the end of curing, we take 7 days. And the depth of the member, we take for a slab 200, 300, 400, and 500 millimeters. And for a beam, we take a depth of 600, 800, 1000, and 1200. The width of the beam is half the height, half the depth of the beam, which makes it a very economical beam. That's why we take half the depth of the beam as the width. And then the perimeter can be expressed easily by a simple formula. And now when we take all those parameters and we do the different calculations, then you obtain all those different dots. The blue dots is for slow aging cement, the green ones for normal, and the other color is for rapid cement. And when looking at this graph, on the x-axis, it's the present code. On the y-axis, it's the new code. And then the black line is where those two values are equal. And we see immediately that for all possible combinations that I mentioned here, that all the dots are above this line. which means that the creep in the new code is bigger than the creep in the old code. It is so for slabs and it is so for beams. And the mean increase, it's a mean, the mean increase is about 7%. So just bear in mind that the creep is bigger than was previously estimated. Then we will talk about compressive strength, FCD, the design value of the compressive strength of concrete equals now NCC times KTC times FCK divided by gamma C. Now, previously it was alpha CC times this. So now you have two elements in it, in the formula. KTC is a factor considering the effects of high sustained loads. So it is one when you have a reference time smaller than 28 days. It's the reference time that you calculate FCK. It's FCK after 28 days or less. Then this factor is 1. That's the recommended value. And if this is not the case, if you define your concrete at a larger or a bigger time, for instance, 50 or 90 days, then you should use 0.85. That's the factor KTC. And NCC of eta CC is a factor explaining the difference between the compressive strength of cylinders and the strength in the structural member. So we do the test on cylinders, but the concrete put in place, like in a slab or a beam or a column, this behavior is a little bit different. And this is accounted for in this eta CC. Eta CC now is a ratio between the reference value and between a reference value of the characteristic strength and the characteristic strength of the concrete to the power 1/3. It must always be smaller than 1. This reference value here is the reference value for eta CC. It's an NAD, so every country can choose. And the recommended value is 40 megapascal. So now looking at this eta CC, and you see here in the x-axis all the concrete grades from 12 to 100 megapascal. And then on the y-axis, eta CC, then you will see that for concrete quality smaller than 40, it's 1, so it does not count. But for high strength concrete, it can go down to 0.75, which is substantial. It's 25% less concrete compressive strength. So we can wonder why is 40 so special? Why not 50? Why not 60? Why not 30? So why is 40 so special? Now you can put it in the formula of FCD, and then you will see the effect immediately. This is the concrete grade, and this is the design value of the concrete compressive strength. From 0 to 40, it is the same. There's no problem there. And the dotted line is in fact what this is in the previous code 2004. But after 40, you have less compressive design value of compressive strength. So why is this? Well, this is because high strength concrete is more brittle. So they accounted for it by limiting the value of FCD. Now the effects of eta CC and on FCD, because it is a huge value and sometimes 25% less. Well, all strength reduction factors in shear force, struts and ties, the nu factor, nu FCD, the nu factor is now simplified. We will see it in later videos. It's simplified because it's a constant value now, not dependent on FCK. So that's an advantage because the lower FCD value is already taken that into account. So that's an advantage. And also for high strength concrete, what they have done is that the strain of the rectangular, the limit strain of the rectangular portion is 0.2%, and from the highest value is 3.5% for the parabolic. So it means that now for all concrete grades, you can use the same formulas because the limit epsilon C2 and epsilon CO2 is the same as for normal concrete. So high strength concrete, normal concrete, those limit of the rectangular portion and the parabolic portion is the same. Then we have tensile strength. We have seen that the formula changed for high strength concrete. Now, this is curious because now the limit is 50. We should expect this is 40 again, like it was chosen in the previous slide, but now this is a different value. It's 50. The formulas are simplified. That's good. That's very good. Just remember that FCTK, the 5% limit is 0.7 times the mean value, and KTT is 0.8, and it's a factor considering the effect of high sustained loads. Then we have the strength classes of reinforcing steel, which is very handy, this table. And you see immediately now that the different strength classes are clearly defined, 400, 450, 500, 550, 600, but they added one strength class, which is P700. So in the previous code, it was from 400 to 600, but now they've chosen specific classes, which makes it easier for us, and added B700. There is also a strength class for pre-stressing steel, which did not exist like this in the previous code. So this is also very handy to define wires, strands, and bars for pre-stressing steel. It makes it clear. Just bear in mind that all the qualities or the strength class, the properties, in fact, not qualities, the properties of the steel, it's only valid for diameters smaller than 50 millimeters. So when you have an exceptional case where you use bigger diameters, you cannot use the formulas of Eurocode 2.